Math 2415, Chapter 10, Vectors in the Geometry of Space, Section 2, Vectors, Video 10, Applications, or more appropriately, application. We're only going to do one example. The difficulty level is about to skyrocket. That doesn't mean we can't do this problem, it just means it's going to seem a lot more difficult than the previous problems. As I mentioned in class, I'm either a physicist or an engineer. Everything I know about either is what I know from teaching Calculus 3. So, but here's a little bit that I know. Here's the scenario. We've got two wires suspended from a ceiling, and they're joined in the middle with a 100-pound weight pulling down on them. And the question is, what are the tensions on each wire being pulled down by this weight? In other words, we want to find these two vectors, both their magnitudes and their components, or, either their magnitudes and directions or component form. We're going to go for component form. So our goal is to find tension 1 and tension 2 in component form. We could also find it in IJ form. Notice I said IJ and not IJK, because we're thinking about this living in 2 dimensions, not 3. So how can we do that? Well, first off, we have to observe that this is in an equilibrium state, meaning that nothing is moving, that everything is remaining static. And so the two tension forces, the two tensions on these wires are balancing the force of the weight being pulled down. In order to attack this, we should probably superimpose this on a coordinate plane so that we can start locating vectors and finding out where's a good place to put the origin. A good place to put the origin would be right here where the two wires meet up with this wire holding the weight. So let's take this and superimpose it on 2 dimensions, on R2 if you will. We have a 50-degree angle here, we have a 32-degree angle here, and how can we represent this weight as a vector? Well, as a vector, pounds is a force. Kilograms is not, but pounds is. So we can represent this 100 weight pulling down as a vector being pulled down whose magnitude is 100. Let's use vector W for that weight. And since it's pulling 100 pounds downward in the negative direction, we could represent this vector as 0, negative 100. We could also represent it as negative 100j. We could also represent it as negative 100j because it's 100 in the negative j direction, negative y direction, As far as the two tension forces, and I wanted to be careful not to draw these vector arrows all the way back up to the ceiling because they're not. The lengths of the vectors are representing the magnitudes of these tensions. T1, T2. I wrote them in reverse order. T1's on the left, T2's on the right. So what do we know about these vectors' sums? Well, we know that since nothing is moving, and so the sum of all 3 of these vectors has to be equal to 0. So we observe that the tension being pulled on the first wire plus the tension being pulled on the second wire plus the weight pulling downwards has to equal the 0 vector because this point where they all meet is not moving anywhere. All right, so where can we go from here? Well, let's see if we can represent T1 and T2 in terms of the angles of the wires that are holding the weight on a ceiling. In order to do this, we need to do a little bit of geometry and a little bit of trigonometry. The geometry is minor. This ceiling is parallel to the x-axis, which means that this line cutting them is a transversal. Ignore this one over here. That means that this 32-degree angle is also down there. Similarly, this 50-degree angle is down here. In geometry, alternate interior angles are congruent. So how does that help us? Well, if we want to look at this in component form, then we need to think about each of these tension vectors in component form. In other words, this T2 vector, let's attack it first. We need to think of it as that vector and that vector. Why? Because its components tell me the displacement in the x and the y direction. So what should we call those generically? Right now, generically, let's just call them x2 and y2. for the distance in the x direction and the distance in the y direction. And let's pull this triangle out. Now here's where I need to be careful. We're about to do some trigonometry. x2, y2, but I can't put t2 there. Because if I'm doing trigonometry, I'm thinking about the lengths of these sides, and this is not the length of that side. What is the length of that side? The magnitude of that vector. 32-degree angle here. Now let's do some trigonometry. In order to connect the first component with the magnitude of this vector, we need the trig function that connects these two. Relative to 32 degrees, this is the adjacent side. We're going to use cosine. We have cosine of 32 degrees is equal to the adjacent side x2 over the hypotenuse, which is the magnitude of t2. This means that x2 is equal to the magnitude of t2 times cosine of 32 degrees. Similarly, if we set up sine of 32 degrees, it would be y2 over the magnitude of t2, and this implies that y2 is equal to the magnitude of t2 times sine of 32 degrees. So we have found an expression for the magnitudes, we found an expression for the components of t2. Therefore, and I'm not sure if I used this symbol in the class the other day, but the 3-dot triangle is a symbol for a math symbol for the word therefore. It means we're about to draw a conclusion. Therefore, vector t2 in component form is the magnitude of t2 times cosine of 32 degrees, comma, the magnitude of t2 times sine of 32 degrees. So we have something to put here. Now, for the magnitude for t1, we could do the same thing, but we need to be a little bit more careful, because if I did the same thing for t1 and put, well, let me write down what you think would happen. Similarly, if you tried to say that t1 was the magnitude of t1 times the cosine of 50 degrees, comma, the magnitude of t2, the magnitude of t1 times sine of 50 degrees, that would not be the correct component form. Why? Both of those components are positive. Magnitudes are always positive, or at the very least non-negative. Cosine of 50 and sine of 50 are both positive, but this vector has a negative x component, which means its x component means a negative in front of it. So how does that help us? Well, that means that we can rewrite this equation representing equilibrium in component form. Instead of writing this vector plus this vector plus this vector and then adding the components, let's go ahead and add them. If I add the first components, the first component of t1 is negative magnitude of t1 cosine of 50 degrees. If I add the first component of t2, it's the magnitude of t2 plus cosine of 32 degrees. Magnitude of t2 times cosine of 32 degrees, plus the first component of w, which is 0. So there's the first component. And then the second component of this sum would just be the sum of the second components. This component plus this component plus this component. So we would have magnitude of t1, sine of 50 degrees, plus magnitude of t2, sine of 32 degrees, plus this component, negative 100. And as much as I hate to erase this stuff over here, it's kind of in the way, it's got to go. So this component-wise represents the sum of t1 plus t2 plus w, and it's supposed to be equal to the 0 vector, and although I don't think we ever said it, the components of the 0 vector are all zeros. Now we have one vector equal to another in component form, and the only way two vectors in component form can be equal is if all of their components are equal. So now we can set this component equal to 0 and this component equal to 0. We have negative magnitude of t1, cosine of 50 degrees, plus magnitude of t2, cosine of 32 degrees, plus 0, so that's gone. is equal to 0. And we have magnitude of T1 times sine of 50 degrees plus magnitude of T2 times sine of 32 degrees. Minus 100 equals 0, but let's go ahead and add the 100 to the other side. Now I'm putting a box around this, and it's not because we're done. I'm putting a box around it for emphasis. What are we trying to figure out? We're trying to figure out what T1 and T2 are in component form. Now, I had it written over there and it's gotten erased, so I'll bring it back over here. T1 in component form was negative magnitude of T1 times cosine of 50 degrees, comma, magnitude of T1 sine of 50 degrees. Sine of 50 degrees. And then T2 in component form was magnitude of T2, cosine of 32 degrees, comma, magnitude of T2, sine of 32 degrees. So if we want to know T1 and T2 in component form, we need to know their magnitudes. Because cosine of 50 and sine of 50 and cosine of 32 and sine of 32, those are calculator problems. We just don't know these magnitudes yet. But where are we? We have a system of equations. We have two equations and two unknowns, and we can solve it. Now it's a little bit ugly, not because of the magnitudes, but because of the trig functions, but it is solvable. Now, by the way, this problem comes straight out of the book. It's on page 548. And it's amazing in this book how the author just glosses over some of the algebra. He basically says, well, if you do this and then you do that, here's the magnitude of T1 and here's the magnitude of T2. But I want to do this problem as algebraic justice and actually solve the system of equations. There's a variety of ways to solve the system of equations. One strategy is to solve one equation for one of its unknowns and substitute into the other. So to solve the system of equations, I think the strategy I'm going to take is I'm going to solve this equation for one of its magnitudes because it's got a 0 over there and that's convenient. If we solve this, if we solve the first equation for the magnitude of T2, it would be actually pretty easy. To solve for magnitude of T2, we would just have to move this term over, which would make it positive, and then divide by cosine of 32 degrees. So solving this equation for magnitude of T2 would give us magnitude of T1 times cosine of 50 degrees, and at that point it would be positive because we would add it to the other side, and then divide by this coefficient of the magnitude of T2, divide by cosine of 32 degrees. Now that we know magnitude of T2 in terms of magnitude of T1, we can substitute into the second equation. In other words, we can go to the second equation and replace magnitude of T2 with all this. So if we go to the second equation and replace magnitude of T2 with all that, we get magnitude of T1, sine of 50 degrees, plus, remember, we're replacing magnitude of T2 with all this. Magnitude of T1, cosine of 50 degrees, over cosine of 32 degrees. So this just got replaced, times sine of 32 degrees is equal to 100. Now we've reduced it down to one unknown, magnitude of T1, and we can solve for it, and it's not really as hard as it seems. First off, sine over cosine is tangent. So I can take these out and just replace it with tangent of 32. I don't have to, but one trig function is better than two. Then to solve for T1, we can factor out the magnitude of T1 and be left with sine of 50 degrees plus cosine of 50 degrees, tangent of 32 degrees is equal to 100. And now we just have to divide by this parentheses. And we know that the magnitude of T1 is equal to 100 divided by sine of 50 degrees plus cosine of 50 degrees, tangent of 32 degrees. And that could go into a calculator and get a decimal approximation. The author does do this, and the magnitude of T1 is about 85.64 pounds. Remember, our forces are being measured in pounds in this problem. And now that we know the magnitude of T1, we can simply substitute it here and figure out the magnitude of T2. Magnitude of T2 would be the magnitude of T1, which was about 85.64 pounds, times cosine of 50 degrees, divided by the cosine of 32 degrees. And if you put that in a calculator, you get approximately 64.91 pounds. Which still doesn't answer the question. The question is what was T1 and T2 in component form? Well, we already know it's equal to these, and now we have the missing magnitude, so we can substitute them back in. Therefore, T1, if you were to take this magnitude, substitute it here and here, and then multiply by the cosine of 50 and the sine of 50 respectively, don't forget your negative, your T1 ends up being approximately the vector negative, where'd it go? Negative 55.05, comma 65.60. And for T2, you would take the magnitude of T2, 64.91, put it here and here, multiply by the cosine of 32 and the sine of 32 respectively, and get 55.05, comma 34.40. I think it's interesting that the x components are opposites. I'm sure there's a physical reason why. Oh yeah, the reason they're opposites is because the weight is not pulling in the x direction. So to achieve equilibrium in the x direction, the forces of the tensions, components in the x directions have to cancel each other. So it makes perfect sense that those x components are opposites. The y components are not opposites because they would have to counteract the force of the 100 pounds going down. And if you notice, the sum of these y components is 100, which means the vertical components of the tensions pulling up matches the vertical component of the weight pulling down, hence we have equilibrium. Well, that was a fun problem. That was a long problem.